education.
All right, cool. Let's get started. Thank you everyone for coming. Welcome back to Machine Learning and Friends Lunch. We've been off for one semester. We've been without pizza and without machine learning for far too long. And to kick this off this semester, I'm very happy to welcome Professor Angela Zhou from the University of Southern California. Angela is an assistant professor at the Marshall School of Business in Data Sciences and Operations at the University of Southern California. Her research interests are in statistical machine learning for data-driven sequential decision-making under uncertainty, causal inference, and the interplay of statistics and optimization. She's particularly interested in applications-motivated methodology with guarantees in order to bridge method and practice. She was also a co-program chair for EEAMO, the ACM conference on equity and access in algorithms, mechanisms, and optimization. And without further ado, please welcome Professor Zhou.
Thanks so much for the introduction. Sorry, let me. Okay, so I'll be talking today about robust fitted Q evaluation and iteration under sequentially exogenous unobserved confounders. And so I know there's a lot of terminology in that second half, which is new, and I'll explain these kinds of modeling aspects that we're going to look at in due time. So let me start by motivating why are we concerned about this causal issue, that of unobserved confounders, which looms really large in causal inference and econometrics and the medical sciences in the case of offline reinforcement learning, which is of course a very core kind of computer science, artificial intelligence, engineering task. And so the motivating question here that, for example, a medical scientist might be interested in is, let's say they have access to a large database of electronic health records, and it records the actions of doctors giving treatments to patients over time. And of course, the challenge is that we only get to observe the outcomes under the treatments that the doctors actually gave. And so this is exactly what we might think of as trajectories from an agent interacting sequentially with the environment. But the principal concern is, how do we evaluate the value of actually different decision-making policies, or in the medical setting, different clinical decision-making rules? And we want to estimate that value so that we can actually optimize it and find optimal decision rules and optimal policies. So this task in general is called off-policy evaluation in reinforcement learning. There's a lot of work in the single time step setting, both on evaluation and optimization. And this is fairly successfully deployed in practice for tech companies, for example, to reuse data from A/B tests in order to determine optimal targeting rules and so on. Now, of course, when there's a finite time horizon, this is the task of offline reinforcement learning. But typically, offline reinforcement learning doesn't account for potential so-called unobserved confounders that may have generated the data. And so this is generally a problem because although we may want to use this kind of rich observational data in order to develop more intelligent decision rules, there can be a lot of issues with working with this kind of data where our assumptions for typical offline reinforcement learning are simply not true. And also, a lot of these environments where we do want improved policies, if we're doing offline learning, it's because our access to online exploration is quite scarce for safety or cost reasons, and we don't actually have a good simulator for the underlying dynamics. And so our only option for validating the efficacy of a given policy is this kind of statistical off-policy evaluation, which is vulnerable to these issues of unobserved confounders. And so there was some controversy a few years ago when it came to evaluating offline reinforcement learning that was exactly using these kinds of convenience medical databases. So what are unobserved confounders? They are unobserved variables that, for example, the doctor that was assigning treatments at different time steps had access to and based their decision on when they were observing the patient. And so it's an unobserved confounder if it affects both the treatment and the eventual outcome. So maybe the doctor has some kind of relationship with the patient. They know how health conscious they are or how likely they are to stick to a treatment regimen, and they take that into account when they're making their decisions. That's exactly the kind of unobserved confounder that will lead to biased estimation for approaches based on direct estimation, and which kind of remove our ability to appeal to causal inference otherwise. And so that's the key challenge that we're going to address in this paper. How can we handle, via robustness, unobserved confounders in more complicated situations of offline reinforcement learning? So in terms of a talk outline, I'm going to first go through the problem setup and also talk about related work and background. Then I'm going to introduce our method and talk about what kinds of guarantees we can prove for it. And lastly, I'll talk about empirics, both with simulated data. We're actually going to work with this mimic sepsis task that kind of motivated a lot of this. And I'll also talk about an extension to warm starting online learning to kind of showcase how our model is different from others. Throughout, the goal is going to be to develop practical methodology for this problem that also comes with good guarantees. And I'm also happy to stop throughout if there are any questions. Okay, so I'll start with the problem setup. First of all, how is it that we're going to model these unobserved confounders in our view of the kind of underlying data generating process? And so we're going to focus on finite horizon Markov decision processes. And the way we're going to model unobserved confounders is that we assume there's some kind of underlying full information state space. We're going to call it S times U, where U stands for the space of unobserved confounders. We're going to assume typical MDP dynamics on this unobserved state space. So at some state S and U, you receive some reward R of S. You take some action A. We're going to consider the case where the behavior policy or the agent that's generating the observational data took actions depending on both S and U. So pi B depends on S and U. And then there's going to be some kind of full information transition probability, which is just a normal transition matrix defined on the full information state space. So the probability of going from S and U to another SU pair. So that's just generic MDP dynamics. We're going to further make an assumption that there's no dependence between unobserved confounders at different time steps, but I'll talk about that in more detail a little bit after I introduce more of the related work. And so again, this task of off-policy evaluation is that I assume that all I have access to is a data set of already collected trajectories from some behavior policy pi B. If I actually observed the unobserved confounders, this would be the same task as normal off-policy evaluation in reinforcement learning, and I could apply my favorite methods. Of course, the challenge here is that we don't observe this full information history. You can think of our observational data set as it's actually just dropped this U column, and all we observe are observed states, actions, and rewards. Ultimately, we're interested in potentially evaluating some other policy, pi E, the evaluation policy. This could be something like a different clinical decision rule, and we want to see if it improves upon the current state of care. Or it could be a sequence of policies that's generated through the policy improvement or other policy optimization approaches. So, of course, in this reinforcement learning setting, we're going to be working with Bellman equations. We're going to this method will work best for binary actions. The value function is the expected sum of rewards, conditional on some state S. The value function satisfies the Bellman evaluation fixed point. And we can also define the Q function, which conditions on both the state and some particular action. So again, there's been a ton of work, either in the sequential setting that assumes that there are no unobserved confounders, or in the single time step setting that allows for unobserved confounders with some robustness. So the main strategy of this work is going to try to allow for as much complexity as possible while staying extremely tractable. And so we're actually going to assume that there's, and so that's what we mean by sequentially exogenous unobserved confounders, that there's one time step of robustness at every point in time. And to kind of summarize our overall approach, that means that it's fairly readily straightforward to consider robust backwards induction, essentially. Okay, and so this is a very, very brief overview of related work. There's a ton of work, very rich literature on off-policy evaluation in finite and infinite horizon reinforcement learning, some of it developed by folks here at Amherst. And the core idea is based on sequential importance sampling, which is a kind of sequential generalization of many ideas that are key in causal inference, which is that we can estimate the importance sampling ratio to adjust for distribution shift from the behavior policy to the evaluation policy. And so that results in trying to estimate this importance sampling ratio, pi e over pi b. And now in the sequential importance sampling, in the sequential setting, this leads to a product of importance samples. So I think there's a typo on these slides. And that tends to blow up the variance over time. There's a lot of refinements as well. You can do more sophisticated things, but typically trying to target this kind of this distribution shift by actions will lead to a very small effective sample complexity. On the other hand, not thinking about off-policy evaluation in particular, the approach we're going to take is based on robustness. And there's also a lot of work on robustness in Markov decision processes generally. So let me highlight some of the differences. Once we translate our problem into a distributionally robust MDP problem, what we're then going to do is actually introduce some additional statistical improvements, kind of again motivated by approaches that come from the econometrics literature to reduce the dependence of our estimating objects like conditional risk measures on intermediate steps. So this work kind of connects robustness to unobserved confounders to risk-sensitive Markov decision processes. So you can also take a look at how this relates to other robust MDP models. So some of the challenges associated with using importance sampling in the sequential setting is this idea of the small effective sample size. Because you're restricting attention to individuals who have followed the same treatment path as you're proposing, in the sequential setting, you simply can end up restricting to very small effective cohorts, which limit the effective sample size of your estimator. And so for this reason, approaches for off-policy evaluation that are based on importance sampling tend to be viewed perhaps as impractical for policy optimization in complex settings. And so, of course, there are other approaches for policy optimization. This is going to be a super brief comparison. Some of them can be model-based in the sense that you're trying to estimate the transition model and plug that into the Bellman equation. Again, in this offline learning setting, this might be biased because you don't have a good sense of how to specify the dynamics. There's also model-free approaches that can be based on policy search or direct policy search, such as policy gradient estimates. These also can introduce some amount of instability, especially in the off-policy setting. So we're specifically going to focus on robustifying the specific method of fitted Q evaluation or iteration, as it's been called recently. And it's related to methods based on approximate policy iteration. So let me first describe what non-robust fitted queue iteration does. And so it's motivated by the fact that the state action value function is the conditional expectation of the so-called Bellman, of the kind of Bellman target. So the current state rewards plus the queue function at the next state. So because the queue function at time t is the conditional expectation of this target, that motivates an approach that is based on regression. So how do we learn conditional expectations? With least squares regression. So stepping backwards in time, at every time step, based on this offline data, we might simply target estimation of the time t queue function by minimizing the squared loss of our candidate regression function, little qt, against this next step target, the rewards plus the next time steps queue function, where we're evaluating this queue function based on what we've regressed previously in this iteration. So in this talk, I'm going to kind of conflate evaluation and policy optimization because we can use, they're quite similar in this approach. If we're just thinking about evaluation, we replace this max over actions by sampling actions according to the policy that we want to evaluate. And if we're thinking about policy optimization, then we have this max over actions. So I'm going to kind of talk about evaluation and policy optimization somewhat at the same time. So that's a very small overview of non-robust fitted queue evaluation. And this is motivated because you can show that even though you are regressing on this Bellman target, you can show that this upper bounds the policy value. And the last thing that I want to mention is that there's a lot of empirical work that shows that fitted queue evaluation iteration can be effective in complex environments. Now, there are definitely trade-offs. There are different assumptions required for validity of these different methods, but there's extensive kind of empirical benchmarking. This is one such benchmark from Fu et al. Okay, so I've kind of described in broad strokes what is the method we're going to build on in the non-robust setting. I'm going to talk in a little more detail about what is the approach we're trying to take for robustness. So the main structural assumption that I kind of mentioned in words before is that the unobserved confounders don't have dependence between different time steps. We summarize this, we call this kind of like a memoryless unobserved confounders assumption. And this is pretty important because this is essentially what allows us to just consider robust backwards induction. So at every time step, we worry about the unobserved confounders at this time step, but we kind of forget about what could be happening, after this time step. So some of our previous work has looked at this for infinite horizon Markov decision processes, but just to summarize, a lot of this work hasn't been really practical for policy optimization. And so that's what we're really targeting in this paper, methods that someone working at a hospital could, for example, deploy. Okay, so that's the problem setup and some related work. I'll talk about our method in more detail, and I'm going to, so there's a few main steps to deriving or motivating our method. The first is the basic idea of using robustness to be robust to unobserved confounders, parameterized by some kind of ambiguity set. In particular, we're going to consider robustness of the Bellman operator, and that's what's going to allow us to translate this problem into the language of robust Markov decision processes, a robust Bellman operator under which we can perform standard operations. And that's how we define our robust fitted queue evaluation and iteration. So first, I'm going to start by introducing the ambiguity sets, or what exactly are we robust to? How is it that people think about robustness to unobserved confounders versus just general robust MDPs? And so the central idea is based on the supposition that we can reason about the extent of unobserved confounding, and that's different from reasoning directly about the transition probabilities. So we can potentially ask doctors, well, how extreme are your decisions differing based on information that isn't recorded in the electronic medical record? How different are they from what we're seeing your decisions being based on average from our observed data? So that's formalized in terms of this weight function, which is the ratio of what we can observe from data, pi b of A given just S, versus pi b of A given all the information, S and U. And the main idea is that if doctors are mostly making decisions based on things like measurements of patient vitals, other information, and the amount of which additional information can change that is not so much relative to what we can observe. If our observed covariates are explanatory of most of the variance in actions, then methods from robustness can allow us to provide guarantees to a kind of last mile of confounding. And so formally, one way to put this into an ambiguity set or uncertainty set for optimization is to assume that the odds ratio of selection into treatment is bounded uniformly by some sensitivity parameter lambda. So now this lambda is essentially a tuning parameter where we can increase the size of lambda. And what that will do is that will increase the size of functions in this set. And so although this expression looks complicated, it induces a kind of L infinity norm on this unknown weight function over the data. And so we could potentially ask doctors and ask them, what are ranges of gamma that you feel are plausible, especially relative to how informative individual covariates already are. So having said this or expressed this in terms of the odds ratio, from here on out, we're going to think about this as simply some kind of linear interval set for this unknown function WT. So this assumption says that WT lives in some kind of interval in between alpha t and beta t. The size of this interval, it does depend on the actual covariates. So it's on the actual covariate as well as the size of the uncertainty set. Okay, so I described the ambiguity sets, and by all means, that's the same ambiguity set that's used in single time-step causal inference. Next, I'm going to talk about a point-wise solution and how we translate that into a robust Bellman operator. So essentially, now that we've said that we think that the weight function lives in some interval set, what we can do is write down a linear program and say that the robust Bellman operator solves can be partially identified with respect to this unknown weight function. And actually, for every fixed state and action, the robust Q function solves this linear program where we're maximizing the conditional expectation. Here, YT stands for the Bellman target, subject to a couple of restrictions. The first is that the unknown weight functions is in this uncertainty set. That's going to be summarized as MSM for marginal sensitivity model, which is how it's called in causal inference, and that the conditional expectation of the weight function given both states and actions equals 1. And that says that the unknown behavior policy actually corresponds to a valid probability distribution. So now our robust Q function for any state and action actually solves this linear program. It turns out that the solution for every state and action is a superquantile mixture. That's not an observation from this paper that has been shown for the single time step case. And we're going to kind of lift that result to the sequential setting using the framework of robust Markov decision processes. So there's a robust Bellman evaluation optimator operator, which computes the worst case evaluation of the Q function over this weight function. There is also a robust Bellman optimization operator, which seeks for the action that gets the best worst case performance. So if we knew the robust function, what we want to do is protect against the worst case situation. So we're going to maximize the minimum of the Q function. Okay, let me describe this pointwise solution in more detail. So yt equals rt plus the Q function at the next time step, either the expectation over actions for evaluation or the maximum over actions for optimization. So this pointwise solution, I said it's a superquantile mixture, which means that it's actually the tail expectation of the exceedance beyond some conditional quantile. So the conditional quantile is defined as the smallest z such that the probability of exceedance of the Bellman target is less than this quantity called the quantile level 1 minus tau. This tau is some transformation of our sensitivity parameter. So the solution to that linear program is an alpha t versus 1 minus alpha t mixture of, on the one hand, the nominal expectation, and on the other hand, the exceedance of the Bellman residual below its quantile level. And so this is a mixture between the nominal expectation and the superquantile. So the superquantile is the expectation of z beyond its quantile. Okay, so the last thing that we're going to introduce is orthogonalized estimation. And so I had to pause and stop and introduce this intermediate quantile ZT that we need to estimate in order to estimate this conditional expectation. On the one hand, the ZT function isn't actually the function that we want to estimate in the end. And so it's called a so-called nuisance function because we have to estimate it along the way to estimate the superquantile. But we really want to target estimation of the superquantile. So one thing that we can do is we can reduce the impact of estimating this quantile z by introducing so-called orthogonalization. And so again, this is actually a really neat idea that showed up in the single time step setting that we're going to lift to the sequential setting. And so what we can do is we can add a zero mean correction term to this term that we're trying to learn the conditional expectation of. So that's shown in here. And it's zero mean, and it turns out that this will actually reduce the dependence of this regression target to estimation error in ZT itself. Okay, and this is a strategy that also appears elsewhere in in single time step causal inference. And so the nice thing is that fitted Q iteration and evaluation is all about regressing onto something to get its conditional expectation. And so we can readily orthogonalize it with similar approaches. Okay, so I'll move into talking about what we can show. And so, for example, we can show that assuming some regularity conditions, we can compare the Q function we would get if we are taking the conditional expectation of this object where ZT is estimated versus if we knew the actual ZT. And so essentially we can get a quadratic rate speedup relative to the first stage estimation error of ZT. And so this says that we could only assume ZT at, for example, quarter root rates in order to obtain square root n convergence. And so that's a kind of nice improvement in the estimation of improvement of this approach. And this is also applicable more broadly to, for example, CVAR Markov decision processes. Okay, so I talked about the pointwise solution to the robust Bellman operator. And so now we can kind of put it all together in terms of defining the robust fitted Q evaluation and iteration. And so again, fitted Q iteration is iterated regression. We can also define infinite horizon versions of this, and everything extends quite directly. Now for our robust fitted Q iteration, we're going to do this robust policy optimization. So find the action that has the best worst case performance. And then we're going to evaluate eventually this orthogonalized Bellman residual. So there's a couple of things we need to evaluate along the way. The first is the normal Bellman target, fit that quantile, and then evaluate that orthogonalized target where we added that zero mean correction. However, given that, we find our Q functions the same way by regression. And what's nice about this procedure is that every step of this is mostly fitting some regression, and therefore it's plausible that someone working in a hospital could go ahead and implement this because everything is a sequence of regressions. Okay, so to summarize how we put the method together, we translated our uncertainty or ambiguity about unobserved confounders into an uncertainty set for optimization. We can then use the framework of robust Markov decision processes to identify this as an SA rectangular robust Markov decision process. We use the closed form solution to the bounds, study it a little more carefully, and are able to show that we can add some additional orthogonalization to reduce our dependence on estimating this quantile. And lastly, we can define a robust fitted Q iteration as a sequence of regressions as a very natural generalization of normal fitted Q iteration. Okay, so I'll talk briefly about the kinds of guarantees that we can show. By all means, this will look quite close to typical analysis of robust fitted Q evaluation and iteration, and part of that is because we've appealed to this robust Bellman operator framework, which preserves some properties of the Bellman operator. So similar to general analysis of fitted Q evaluation and iteration, there are two main assumptions that kind of loom large in terms of our ability to provide guarantees. So I'll state them kind of very informally first. The first is that of concentratability, which is like a sequential generalization of the overlap assumption in causal inference. It's satisfied, for example, if we can assure that the states that we would visit potentially under all policies of the policy optimization process are states that we've seen before. Otherwise, we might start extrapolating, and then we would run into issues and saying that our regression on distribution shifted data can apply more generally. The second is that of approximate completeness, which is related to the specification of the regression class that we're regressing onto. And it approximately says that the robust Bellman operator is approximately closed. And again, these are strong, but fairly standard for analysis of FQE. So more formally, we assume that the supremum of the density ratios of state visitation are bounded. And for completeness, we assume that there's some approximation error as we range over functions in the regression class. Okay, so in terms of sample complexity, assuming both of these assumptions and that our regression classes for quantiles and robust Q functions has restricted functional complexity, we can essentially show that we can obtain root n convergence. Root n convergence for the policy value up to some constants such as this concentratability coefficient, as well as the size of the uncertainty set. So as we make the uncertainty set larger, we increase the variance of our estimation as well. And you can think about that as a kind of bias variance sharpness trade-off, in the sense that what this characterization shows is that as you're trying to be more robust, you're actually trying to estimate more in the tails. And you should expect that your estimation error will degrade as you start focusing more on the tails. Okay, so that's the broad overview. We also look at some other quantities like how far is the robust Q function from the nominal Q function under simplifying assumptions such as Gaussianity. Something that I'll talk about after I show empirics for this is something that's very nice about our model, because we do have to make this restrictive assumption about unobserved confounding not being dependent across different time steps, is that you can actually directly use this to warm start online learning. So I didn't go into a ton of detail about other related work. There are other approaches to this problem. For example, one natural approach is, why don't we think about this as a generic POMDP? And so there is really interesting work that studies this as a POMDP. But essentially what we show is that if you assume that the unobserved confounders are memoryless, if you assume more structure, your corresponding online learning problem is actually just a normal MDP. So there would be no issues if you had online exploration and your evaluation policy simply didn't use the unobserved confounders. And so that's the kind of last thing that I'll talk about is implications of this model for kind of other algorithmic ideas. So I know I talked a lot in abstract terms about the method and the model. So now I'm going to show you what this looks like on real data. So the first setting is going to be a simulation with linear transitions. And what's happening here is that as we're going down on the rows, we're increasing the size of the sensitivity parameter. We're going to compare the non-orthogonalized version of this robust approach to the orthogonalized version of this approach. And just normal FQI corresponds to choosing lambda equals 1. And so we'll compare both the error in estimating the average initial value, as well as the percentage of time that you take the wrong action, which is more of a policy optimization measure. And so what we can see is in this setting is that because the conditional quantile is a little bit misspecified, there's heteroscedasticity. Actually, our orthogonalization kind of helps us stabilize this. Because another issue with sequential approaches is that the bias can accumulate quite badly over time. And so we see that as we increase the sensitivity parameter, the non-orthogonalized version, its error actually does increase because of this model misspecification issue, but the orthogonalized version can remain fairly stable. Okay, so that's a kind of simple linear simulation just to highlight the basics. Next, we're going to look at more complex data. So I kind of flashed this slide in the introduction about the AI clinician and some controversy. There was this task, there is this task based on a large electronic database of critical care electronic health records. So that database is called MIMIC, and it's a huge boon to machine learning and healthcare. It makes possible a lot of research that wasn't possible before. But unfortunately, it's also completely collected from the, just the actions of doctors as they are. And so it is, in fact, subject to these concerns about unobserved confounding, because it's neither a randomized controlled trial nor a kind of designed cohort observational study. It's just a database that exists that they made available. And so the specific task is managing sepsis, which is an acute critical care condition and is one of the largest drivers of medical costs and mortality in the US. We're going to follow a pre-processing from a previous data set, but the basic task is that you have a two-dimensional action space. It's discretized. And so the actions are increasing dosage of vasopressors or increasing dosage of IV fluids. And so sepsis is a really, really difficult and complex condition. There are not across the board clinical decision guidelines. It is viewed to be a kind of dynamic and sequential problem, in the sense that, for example, the time horizon for this from previous work was over the course of 72 hours. So there's a lot of continuous monitoring of patient vitals. There is also some idea of really trying to target the levels of dosage, in the sense that there's some agreement that giving nothing is bad, but also giving too much fluids is also bad. And there's also a lot of uncertainty or a lot of conjectures about when is the right time to give vasopressors or fluids. So this is a dynamic problem, but it is very complex. Our reward function is, we're also following this pre-processing of prior work. So -1 is death, all other events are 0, and reward is positive if you leave the hospital. The time horizon we use is 20 time steps, and state variables include both kind of patient context, baseline information like demographics, versus dynamic vitals, which are kind of like updated clinical vitals like blood pressure, oxygen levels, and so on. And so that's a kind of brief overview of the setup. This is set up as a kind of 20 time step Markov decision process. Okay, so first let me show you the distributions of the value functions. So evaluation is going to be taking the average of this distribution, but it will also be informative to take a look at the entire distribution. So the first plot we have on the left is the histogram of time 0 optimized value functions if we assumed there was no confounding. So we're going to call that the nominal value function. And we see that there's some variation, and this is also very heavy-tailed data. So the middle plots is going to show the distribution of our robust value function with a sensitivity parameter of 2. And so what happens is that the robust value function actually kind of goes more towards the extremes in a relative sense, in the sense that it's way more pessimistic about more individuals. In the sense that it's much more pessimistic about more individuals. We truncate this plot because when you're estimating quantiles over 20 time steps, the tails do grow quite a bit. And so the robust value function is much more pessimistic, but what we can also do is we can use robust evaluation to evaluate the worst case performance of the naive policy. And so, of course, the naive policy is going to be worse under worst case evaluation. but still we can show how much worse it is. So this black line on all of these plots shows the mean estimate. So the nominal value function's mean dropped to 0 for the robust value function. And when we evaluate the worst case performance of the nominal policy, it does do worse. And this is how much worse in a sense. So that's a comparison of the value function distributions. Of course, with this data, we don't actually have the ground truth to compare. So we can't say what is necessarily best. Another thing we can do is try to interpret how is it that these robust policies differ from their non-robust counterparts. So here's a summary plot that's trying to summarize how the actions that the robust policy takes change as we change the sensitivity parameter. And so for simplicity, even though this is a 5x5, 25 grid action space, we're going to kind of summarize these actions into pairs of vasopressors and fluids that essentially correspond to being nearly untreated in blue. So very low values of both, only vasopressors. So giving some moderate or more amounts of vasopressors, but no fluids. Only fluids, so giving some amounts of fluids, but no vasopressors, and the combination of both. So we're going to define kind of like 4 quadrants of this 5x5 grid. And so what we see is that the percentage of patients who go untreated increases as we're becoming more robust, but also the percentage of patients who receive both vasopressors and fluids increases as we're becoming more robust. So this is to summarize a lot of kind of complex information, but in very broad strokes, as you're becoming more risk sensitive, you may actually default to not providing to very low levels of treatment to reduce the variability in outcomes, essentially. But you're also going to increase the intensity of treatment to try to prevent worst case outcomes. And so that's what we're seeing when the percentage of vasopressors and fluids increases. So that's the empirics for this specific method. We saw in a simulation that orthogonalization is very helpful. And we also saw that this does kind of scale to more complex tasks that have been of interest previously. Okay, so the last thing I'll talk about is this extension that we can study about warm starting online learning. And so the main assumption throughout this paper was that there's no dependence between unobserved confounders at different time steps. And so what this means is that this is actually much easier than a generic POMDP. So this extension kind of also helps us show like how much easier. And the basic idea is that we're going to warm start just a generic reinforcement learning algorithm. The basic idea, which is a generalization of some ideas about warm starting tabular reinforcement learning, are that we're going to reduce the amount of optimism in the online algorithm given valid bounds from our observational data set. So I won't go into too many details, but basically, if we have a large observational database with infinite data, and if we knew that we had appropriately selected the gamma parameter, then we have robust bounds on the true value. And so our warm starting is going to choose the minimum of the online optimistic value function from the RL algorithm and the valid robust upper bound from observational data. So this means that in the very beginning of the approach, we're not going to be as optimistic as we would be in online learning. And part of that is due to using this prior knowledge. So you can think about this as incorporating a prior. And the main idea is that this will maintain optimism and reduce our contribution to regret. So I'll just show a plot. On the left hand is what happens if you do something super naive and you just use your confounded data and your regret is absolutely terrible. That is kind of a straw man. So let's focus on the right plot, So if you do have access to online exploration, what you can do is just run a normal RL algorithm. That's in orange. But we see that our warm start procedure can actually improve, especially in the early phases of learning. Okay, so there's definitely a lot more to do there and to characterize, but the main thing I wanted to show is just that the specific assumption that we're making, that there's no dependence between unobserved confounders at different time steps, kind of buys us a lot. And there's interesting things to think about along these lines. Okay, so I'll conclude there. These small bounds can help robust decisions and inform better data collection. Okay, and thanks so much.
I think I'm off camera, Angela, but very nice talk. Can you hear me?
Oh, yeah.
Okay, wonderful. My question is actually about that assumption about uncorrelated confounders. Because you cited an interesting example at the beginning of your talk of a doctor may choose a particular course of treatment because he or she looks at the patient and says, I think this is something about the patient makes them believe that they would follow a complicated course of treatment, whereas they might not prescribe that if they didn't feel that the patient was able to do that. And that's something that's likely to persist across a set of treatment decisions by the doctor. Both it's going to influence the treatment, it's going to influence what happens to the patient. So is there a sense of that those don't happen frequently, and what would happen if there is sequential correlation among the confounders?
Yeah, that's a very good question. So you're right to point out that that example is actually not the best suited to the specific form of this assumption. So that kind of baseline confounding is very interesting, but it is actually kind of much more difficult in this framework, because it does introduce dependence across time steps. So a more appropriate example is something perhaps related to measurement error. So something like a doctor was trained with a certain kind of clinical decision rule based on something that's not measured. And so at every time step, depending on the value of that unobserved confounder, there could be a different decision. The case of baseline confounding is interesting. I think there is a difference between the stationary setting and the finite horizon setting in that case. But it actually is much harder to kind of to couple the uncertainties across different time steps, because that doesn't allow the same robust backwards induction. Now, something that can always be done is ignore the sequential dependencies and essentially solve for robust rules with robust backwards induction. And that actually corresponds in a certain sense to like a relaxation of the assumptions on the baseline confounding. If you think about what that means, it does feel very conservative. You can think about this as like, you can think about that as making like 10 copies or T copies of the baseline confounder, which does feel pretty conservative as an approach, but that is what would happen.
Thank you.
Can you hear me?
Yeah.
Okay. Sorry. I just had a question about like somewhat related, but because like confounders are often not observed, but there's like methods about like detecting that there might be confounding going on, even if we actually do not necessarily observe it. So like just like kind of a hypothesis checking or model checking sort of thing. Like I was just wondering, do you have any ideas about like can we verify some of these assumptions? Maybe, just like what you said, can we verify that if the confounders existed, they are like uncorrelated maybe?
Yeah, that's a great question. And so unfortunately, because unobserved confounders are an assumption about the joint distribution of causal outcomes, they're generally not testable, but there's a couple things you can do. One thing that would be interesting is that there are now a bunch of different methods for this problem with different assumptions, like instrumental variables or proxy causal inference and so on. And so you can actually develop so-called falsifiability methods based on these different assumptions, in the sense that if there's an IV, you could compare the bounds from the IV to the bounds from this approach. And if those bounds cross, you know that one of those assumptions is wrong. So there are falsifiability strategies when there's kind of like multiple potential assumptions, and that is possible, but it's not generically, unfortunately, it's not generically possible to test for unobserved confounding.
So I've got another question about sequential treatment plans. My vague understanding of medicine is that often doctors have sort of treatment plans, standard treatment plans that they execute. And that would, it would seem like that would cause a kind of positivity violation, in the sense that you wouldn't see all combinations of treatment choices. Is that something that happens, and what do you do about it?
Yeah, that's absolutely a great question. So you should think about this class of approaches as appealing to some kind of randomization in the doctor you see, and kind of like perhaps where they trained. So there might be different kinds of clinical decision rules, but we are kind of assuming under the hood that there is variability overall. So maybe people were trained with different clinical decision rules, and that leads to variability. And another thing to consider is essentially the state of clinical consensus on any given problem. So I'm certainly by no means a doctor, but there is no clinical consensus on how to treat sepsis currently. And so although that is very difficult from a clinical point of view, it does mean that randomization and seeing different decisions in our underlying data is more plausible in this particular setting. But that's a great question.
Well, might it be possible for reinforcement learning approach to sort of come up with a super policy that had never been tried before?
Yeah, that's generally possible, but my sense is that that would be difficult, that would be less palatable to doctors. So there's definitely a ton of really interesting translational issues and a lot of interesting questions of how can you kind of validate these rules with expertise, or especially with imperfect expertise, essentially.
Cool, thank you.
Okay, thanks so much again.
Okay, let's thank the speaker for the great talk and the great discussion.
We have a break for about half an hour, after which the first one-on-one meeting starts at 1:30, and there was a link put out on this site that just wants to meet for one-on-one.
Great. Okay, great. Okay, sounds good. All right. Thanks so much again.
Yeah.